With the old type A meter, the meter man didn't have much trouble connecting the load wires into the meter. Wires from the meter to the fuse block were readily accessible and could be easily looked at. If he made a wrong connection when he closed the knife blade, all that happened was blow the plug fuse and out went the lights. The fault currents available at this meter in those days were very small. There wasn't a serious problem if he made a mistake in the wiring. But then we developed the meter socket, and with the meter socket came hidden wiring. We noticed this meter man as he puts in the meter. He has to look at the side, tip the meter, and then beat it a little into the socket. Also, we noticed that the meter man did not do any checking before he installed the meter. Fault currents have risen right along with the capacity of the meter. In some location, the fault currents are over 500% what they were 20 years ago. 5,000, 10,000, 15,000, and even higher are common figures in our distributions today. This is a picture of a 7-terminal self-contained polyphase meter. It's a picture of a fault that started with a single phase to ground and then developed into 3-phase. A similar accident happened at the Oklahoma Gas and Electric Company. Arrangements were made with the Square D Manufacturing Company in Cedar Rapids, Iowa, to use their test facilities at their short-circuit test lab. Here, we could take pictures of what really happens when a meter is put into a socket and causes a fault. We could take high-speed movie films and measure the current that flows through the meters to get an idea of what really happens in our meter installations. Russ Shope is in charge of the test lab for Square D. Here he meets Mr. Veely, Mr. Young, and Mr. Woodson of Iowa Electric Light and Power Company. In the test laboratory, a device was made that would simulate a man putting a meter into a socket. An air plunger held the pressure of the meter going into the socket for 22 cycles, typical of the action of a man. The automatic control console allowed us to program the installation of the meter, the load at the meter socket, the availability of the power, and a oscillograph record allowed us to measure the current magnitude. All was programmed so that we could apply the power to the meter socket for 30 cycles. Earlier in the film, we saw this 3-phase fault that happened in Oklahoma Gas and Electric. And here we see a slow-motion picture film taken at 3,600 frames per second to show what happens in the 8 cycles it took for this meter to burn in the clear. This fault started with a phase to ground. The ionized gases carried the fault to a 3-phase fault. The bright specks you see going across the screen are hot, molten copper. Most of our test faults cleared in 8 cycles. We get a close-up view of the mannequin that we put alongside the meter socket to represent a man installing the meter. We see that his shirt is burned. There are some dark specks on his hand and face. The terminals in the meter are burned completely. Here is a 3-phase transformer bank installation that has 5,000 amps of fault current available at the secondaries. There are houses served from this same transformer bank. When a meter man walks up to this meter installation and installs a meter into the socket, he has available at these terminals a fault of 5,000 amps. We took a slow-motion picture of a Class 200 meter installed in a heavy-duty clamp-type terminal socket. There are approximately 11,000 amps flowing through this meter. We took this to prove that a meter could stand up to 11,000 amps flow-through current without any readily apparent damage. We realized that meters and meter sockets are not made to be a fuse device nor a disconnect device. Nevertheless, with the currents that we are dealing with today, we must have these meters capable of handling the currents that we are applying to them. If a meter man installed a meter into a socket where there was only 5,000 amps fault current, it would probably look like this. It doesn't seem to be much, but when we take a slow motion picture of what really happened in this 8 cycles that it took this meter to burn clear, we see quite a display of ionized gas and molten copper. We don't expect meter sockets to stand this kind of load. We realize they are not disconnect devices and are not made for this type of application. But when the meter has to be tilted in order to line up the meter terminals with the meter socket, we are endangering a phase-to-ground fault with almost every installation. Our meter men should be thoroughly trained to check the installation of the meter socket and wiring before the meter is put into place. Here is a typical installation in Cedar Rapids, Iowa. There are 15,000 amps available at this 5-terminal, 3-phase, self-contained meter. The fuse device is questionable should it be able to interrupt 15,000 amps. If a meter man tilted this meter and caused a phase-to-phase fault, he would have 15,000 amps blow up in his face. Here's another typical installation in a business district. There are 15,000 amps available at these secondaries. When we go inside and take a look at the meter, we see an old-style self-contained meter with an old-style fuse disconnect. Will this disconnect interrupt 15,000 amps? This is what a 15,000 amp fault looks like when you put a meter into a socket. When we look at a slow motion picture, we see what really happened in the 8 cycles it took for the meter to burn clear. We begin to realize the magnitude of 15,000 amps fault current. The molten copper that you see going down across the screen will burn a man severely. We suggest that no meter socket is used, single or 3-phase, without a clear plastic shield to guide the terminals of the meter into the socket directly, without allowing the meter to be tilted or causing a phase to ground, or, in the case of many 7-terminal meters, a phase-to-phase fault. Some circuits that we meter with a self-contained meter have available to them many more amps than this 15,000 that we have seen here today. Some of them are fed from much larger distribution transformers. Here's a typical installation of a transformer in a vault. Directly from the secondary terminals of the transformer, we take cables along the wall of the vault, through the vault wall into a cable raceway, and directly into a self-contained meter. It is true this meter can probably meter the 200 amp load, but also at the terminals of these meters is a fault current available of much greater than 100,000 amps. The fuse disconnect on the secondary side cannot interrupt a 100,000 amp fault. If a meter man installed a meter into this fault, it would look like this. Notice the meter become a projectile and knock over the lamp. When we look at this in slow motion, we see what really happens during the 8 cycles it takes this meter to burn in the clear. You will notice as the meter becomes a projectile, you can see in the smoke where it leaves the holding apparatus and the brilliant display of the molten copper that is flying in the area. We don't expect meters to be able to stand 100,000 amps, but we do suggest that the fault current be one of the considerations when we meter a customer's load. And any meter installation that has available at its terminals 10,000 amps or greater should be transformer rated. When we look at this mannequin, we see that his shirt is completely burned. A portion of it is blown away from the body. The meter socket is burned up, his neck is burned, his glasses are burned and charred. it is doubtful that a meter man, had he installed this meter, would have been able to survive. This is a self-contained 440-volt meter. Theorizing that a meter man had caused a phase-to-ground fault, the ionized gases took this into a three-phase fault. All the rest of our tests cleared in 8 cycles, but this test did not clear until we shut the power off. It held for a full 30 cycles, indicating that it would not break the arc until the primary source was disconnected. You can see the pulsations as the current goes through the sine wave 0. We would suggest that no self-contained meter be used on 440 volts and above, that they be all transformer rated. You can see that this fault is still in effect. The meter and the terminals were completely burned up. Sometimes we use the old converted watt-hour time switches to meter loads. Here we have 5,000 amps flow through and 2 different tests showing that these meters will not stand this type of fault current. We would suggest that we do not use these meters where the fault current is above 1,000 amps. The ionized gas builds pressure within the meter and explodes the meter glass. As we look at this in slow motion, we can see gas develop within the meter cover. And you can see the glass begin to crack and shatter before it explodes. These meters were not designed for our interrupting capacities that we have today. Anytime we use a heavy-duty socket, we should not compromise for a cheaper brand. We should use the type that have protective shields and clamp-type terminals. Here's a 15,000 amp flow-through test on a Class 200 heavy-duty meter. You can see that this meter will not stand 15,000 amps flow-through. We are not suggesting that any meter should be able to stand this much current. We do say at this time that when your fault currents available are greater than 10,000 amps, it should be transformer rated. Notice this slow motion picture of this same 15,000 amp flow-through. Look at the vibration of the meter register. Then you can see the ionized gas begin to build up inside the meter cover just before it explodes. This took approximately 15 cycles. When we look at a customer's load and we make a decision on how to meter it, the decision that if it is 200 amps or below is not the only thing to take into consideration. The available fault current must be calculated and consideration must be taken that if it is over 10,000 amps, transformers may be the answer. Our meter men must be thoroughly trained on how to check out a meter installation before they put a meter in a socket. These fault currents that are available at the meter sockets have grown past the value of our realization. You will notice that this meter did not leave the terminals of the socket. If we would have used a converted watt-hour time switch at the same location, it would have blown up in something like less than 7 cycles, and this is what it would have looked like. Obviously, this is an improper meter application. When a meter man goes to install a meter, he should disconnect all of the distribution load from the junction boxes. Then he can go back and properly check out the socket installation. He can check his source to make sure that he has the proper voltage. He can check the secondary to see that he hasn't any voltage feedback. He can check the secondary terminals so that there isn't any short. He can check the secondary leads to ground to make sure that they are not grounded. And after he is satisfied that it is properly wired, he can then install the meter. But here again, you'll notice, he must tilt the meter. Look to the side before he can put the meter socket into place. If we would have had a protective shield, he could have guided the meter directly into the terminals of the socket without tilting the meter. We must stress that training our meter men is a must in today's high fault current availabilities. For some reason, the safety director is smiling. How do you stand in your system? Have you checked? Do your meter men check? Are you using the proper application for self-contained meters?